All right, this time we'll talk about waves and oscillations. Um, Obviously, there's different forms of waves out there. There are sound waves, light waves, water waves, all sorts of different waves. But they basically all come in two different types. There's what's called longitudinal waves, and then there's transverse waves. And the difference between these two is longitudinal is a wave where the oscillations are in the same direction as the motion or the traveling of the wave. And so that's what a sound wave is. For instance, sound wave is longitudinal. What happens with a sound wave is as you talk and you have your air molecules in front of your mouth, you basically push air molecules next to each other. And then those molecules push the next ones out and they spread out. And then they get closer together. And they spread out. And they get closer together. And this is happening in the direction that the wave is traveling. The other type, of course, is transverse. And a transverse wave is one in which the oscillations are perpendicular. And so this is like water waves and light waves and things like that. With a water wave, of course, the wave looks like this in the water, and the wave is traveling this way towards the beach. And you see the oscillation of the wave is occurring up and down, but the motion of the wave is occurring to the right. And so that's a transverse wave. All waves will have the same main characteristics. And those characteristics are frequency, wavelength, and speed. These are the big characteristics of waves we're going to have to know. And of course, we're going to want to know how they relate. Well, frequency, variable for frequency is f. Of course, sometimes you also see it as the variable nu, depending on which physics textbook you use. The units of the frequency is 1/seconds, which is called a hertz, capital H, little z. And basically what frequency is how many oscillations occur per second. So, if we think about something like light, light, of course, is an electromagnetic wave. That means it's got electric and magnetic fields that are oscillating up and down or back and front or whichever directions they're oscillating. And the frequency of light tells you how many times the electric field oscillates up and down in 1 second. So it could be, 60 hertz or 14 trillion hertz or whatever the number is for this particular wave. The frequency is how many times it goes up and down per second, basically. Wavelength, its variable is lambda, Greek letter lambda. The units, of course, are meters because it's a distance of length. And wavelength is very similar to frequency in some ways. If we look at a wave, let's say this is a wave here, the wavelength, if this is a plot of the amplitude versus distance, so as a wave is traveling to the right, let's say, it's oscillating up and down. The wavelength is defined as the distance the wave travels in making one oscillation. Distance traveled in one oscillation. So, for instance, if it starts here, it goes up, down, and back to the beginning again. This distance here, that's one wavelength. Notice it's not from the beginning to this node here, because the starting point is it's at the 0 point and then it moves upwards in its wave. Whereas here it's at the 0 point but it's moving downwards, so it hasn't quite done a whole oscillation. It's done a whole oscillation by the time it's reached back to the same as the starting point, and it's moving in the same way as the starting point was. So wavelength and frequency, they're very similar, except frequency, of course, deals with the time it takes to do an oscillation, whereas wavelength talks about how far a wave goes in one oscillation. Of course, speed being the last one, well, that's usually V, is for velocity. Any units are meters per second. And of course, we understand what speed is. It's how fast does the wave travel. You know, it's going 60 miles per hour or 60 meters per second or whatever. Now, there are two other little characteristics we could talk about which relate to these. The first being called the period, and it's related to frequency. The period is capital T, and its units are seconds. And it's defined as 1 over the frequency. And what the period is how long does it take to make one oscillation. So very similar to frequency. Frequency is how many oscillations happen in 1 second. The period is how long does it take to do one oscillation. So, and they're related by, of course, this equation right here. If you know the frequency, then the period is just 1 over the frequency. The other thing you may want to know is called the wave number. Its variable is K, and its unit is 1 over meters. And it's defined as 2 pi divided by wavelength. Now this equation, this wave number thing, is purely a matter of making some equations we're going to see later look a little nicer. Okay, so it's not as important. Wavelength makes sense. It's how far does the wave go in doing one oscillation. Wave number is just kind of a manipulation to make an equation easier later on. All right, so with that, the first big equation we have is the relationship between the speed, the frequency, and the wavelength. And it's pretty easy. It says the velocity of a wave is the frequency of the wave times the wavelength. Really easy equation. And in fact, we could see that must be true because if you remember the units of frequency, that was 1 over seconds. Wavelength was meters. And so, of course, we get meters per second as the units for velocity. So dimensional analysis could have given us this equation. Well, this is nice, and this is true for all waves, whether it's sound waves, light waves, water waves, any kind of wave you can think of, they all obey this equation. And so if we're talking about light waves, then this equation is made a little bit more special for light. It says C is frequency times lambda, because C is the speed of light, and this is a constant. 3 times 10 to the 8th. And it's always this number no matter what. And so the frequency and the wavelength will change so that the speed of light is always the same number. With other waves, like water waves, of course, the velocity can be different. It doesn't have to be a constant number. So a lot of equation or a lot of problems we're going to have will deal with you being able to, what's the velocity of a wave whose frequency is blah, 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 and whose wavelength is 3 meters? Or what must the frequency of light be whose wavelength is such and such? You're going to make use of this equation here to solve those types of problems. And they're pretty basic. They're pretty much plug in the numbers you know from the equation into this, from the problem into this equation, and you'll have your answer. The big key, of course, is making sure your units are correct. Frequency must be in hertz, wavelength must be in meters. All right, another big equation is kind of the mathematical form of a wave. And so if we're going to describe a wave in physics, and of course math is the language we use for a lot of our work, then we need to know how to define a wave mathematically, as if we're going to draw it out on a coordinate plane or something. And the equation goes like this: y equals a sine 2 pi f t minus 2 pi over lambda x. So let's talk about this. This y is basically the height or amplitude of the wave at some time and place. So say, for instance, we have, the ocean, and we've got waves in the ocean, and we got the beach over here. Then I can ask, well, okay, what would be the height of the wave at this point, so this place, at time t is equal to 3 seconds, or whatever time we want to talk about. And this equation should be able to tell us exactly that. So the y is, what is the height of the wave? It's also called the amplitude. What's the amplitude of the wave if I choose this green point, that place in space, at this time, whatever I choose? A, in my equation, that's the starting amplitude. It's also called the maximum, because, of course, since it's multiplying a sine function, and the biggest a sine function can ever get is 1, then the biggest my y can ever get is A. A is as big as this can get, so sometimes we call it maximum amplitude, or the starting amplitude of the wave. That is, what's the biggest height my wave can ever get. Then, of course, here we have frequency, f. T, that's the time I choose to look for this wave. Here's lambda, the wavelength. And x, that's the space point I choose. So this green point here. Let's say that's at the x equals 5 meters mark. Then I'd put 5 in for x. So t and x are things I have to put in, whereas f, lambda, a, those are things that are specific about the wave. Those are details I need to know about it. If I know all that information, then this equation will be able to tell me the height of the wave at any point in time. That's what y would be. Now we can see this is kind of an ugly equation because of all the 2 pi's and stuff, and that's why the wave number was invented, to make this look a little nicer. And so what we do is we rewrite the equation y equals a sine, and then what we do is we say, look, let this 2 pi f thing, let's call it a different variable name so I don't have to write 2 pi f every time. And so they call it omega, which is called angular frequency. So the angular frequency is just a linear frequency, the f that we knew from before. You multiply it by 2 pi, and now you call that the angular frequency, omega. So we got omega times t. And then, as I said before, this 2 pi over lambda, that thing I'll call k, the wave number. And so when I put it in my equation, this just becomes kx. And now we can see this is much prettier of a form than it was before. And physicists and mathematicians do this all the time. They get the ugly true form of the equation. They make some different variable choices. They plug in different variable names so that it looks nicer. They substitute in. And so that's what we have. And so with this equation, basically what you have is problems where I say, okay, here's the form of the wave, this equation here. I'll have numbers for the a, for the omega, and for the k. And I can ask questions like, okay, what's the maximum amplitude? Or what's the frequency of this wave? Or what's the wavelength of the wave? Or I can ask, what is the speed of the wave? For instance, now that I have my omega and my k, if you remember the equation, v is f times lambda, well, now this equation becomes v is omega over k. Replacing omega and k with the other form, 2 pi f and 2 pi over lambda, you get back to this equation again. So if I give you numbers for omega and k, you can tell me the velocity of the wave. You just divide the angular frequency by the wave number. And so that's basically the first types of problems we're going to be working with. So I hope this is helpful.